seen these amazing images on all over the internet. I mean, it's going viral everywhere. But like, how does it actually work? I mean, it's all good entering the prompt into some obscure website on the internet, but what's the technology behind it? So, are you guys recognizing any of these? DALL-E 2 is a pretty famous one. Anyone? If you put your hand up if you recognize DALL-E 2? Awesome. And of course, Stable Diffusion. I mean, that's why we're here. Don't know why we'd be here if you didn't know. Mid-Journey. All the other ones are basically run by corporations. So maybe there's some kind of free version or unofficial version, but they're all charging money. But Stable Diffusion by Stability AI is under this special, I forget what it stands for, reliability, well, it's real M license, so it's open to use, as long as you basically update to the newest version. There are small differences in between these models, so you can see here Google doesn't generate the final image. It creates this smaller 64 by 64 image, and then it upscales it to the final one. So, Stable Diffusion. First, of course, we start by entering a prompt. If you see now the websites, but we train these models by adding noise, Gaussian noise. So progressively, we give it basically a bunch of images on the internet. We scour the internet for images, we give it a shitload, and each one of these images, we add a random amount of noise to it. And the model just wants to reduce this noise. Of course, when we're training it, we completely mix up complete random order. So the model has to figure out by itself what the hell is looking at. And when we get that noise, the model, of course, tries to denoise it, reduce that noise into something that us humans can nicely look at, right? And the big thing here is the model doesn't predict the image, it predicts the noise. And then the noise is taken away from the noisy image. If that makes sense. And we'll come back to that later, it's quite vital. So, I'm sure you're wondering where the hell this prompt comes into it, but we'll get that at the end. So of course we're here, we'll start with the unconditional image, which is any kind of noisy image. And then, as I said, we predict the noise, not the image, the noise. And we take away this prediction from the noisy image to go our final image. Any ideas why we do that? So, if you think about it, if the model only has to predict the noise, it doesn't have to remember the content of the image. It just looks at what it thinks the object should be. And, well, this color slightly changed, so I'll just take color this away. It doesn't have to remember what Shrek looks like. It just has to remember that Shrek is green, and this shade of green isn't the green I want. So you may be familiar with GANs, style GANs, with those like fuzzy face images generated like a couple of years ago. It's somewhere in the same area. It uses a technology called generative adversarial networks. So you can imagine this is basically like two people fighting. You have the generator, or also known as the decoder, and this tries to produce the images. So you get this random noise. From that noise, it gets an image. Then this fake image is given to the encoder, which then basically, or the discriminator, and that tries to tell you, is this a real image? And if it's not, so the more data you give it, the better each of the generator and the discriminator get. But this approach has its limitations. As we saw, that those fuzzy face images aren't perfect. Latent diffusion is better. Yes, double technology. So we covered diffusion models, but what's the latent mean? Well, the latent is like a vector from produced by the encoder, what we saw earlier in the GAN. It's basically like a compressed version of reality into some latent space, vector space, something abstract like that. So we don't have to look at real data, we look at the simplified form. Now, this vector obviously is a lot smaller than the image. So it's going to make our models a lot faster than processing a whole image. So we're compressing reality to make our model faster. And of course, this is done by an autoencoder called CLIP, or it stands for Contrastive Learning Image Pre-Training. So as humans, of course, we see, hear, feel, we have all these different modalities. Now, the best AI wants to combine these now. We don't want just text, we don't want just images, we want a combination, like our brain. So we combine both of these, CLIP combines both of these modalities into the same space. So now we can compare images to text, to their semantical meaning, and we can leverage that in our model with our prompting. Now, another important, I guess now we're making it better by adding the latent. Another point is the variable autoencoder, a slight alteration of the autoencoder before, where in this case the model tries, the goal is to convert that. If you remember back to the GAN, we had the encoder decoder. This is the encoder, right? So we have the latent back to the image, the generator. So this is literally taking one of those GANs and just using that front part of generating images. So we have this latent onto our images, because once we use CLIP to get our noise into a latent space, we have to go back again, right? Otherwise, because I mean, as good as an unnoised latent is, we can't look at it. So we train it back to, we convert it back to an image. So we've covered the CLIP and the variable autoencoder. But this, so as I mentioned before, we had the noise through the diffusion process. That's the proper name for it. So this is just iterative amounts of Gaussian noise that are added on top of the image. And the reversal is done by this thing called a U-net. Now, it's very creatively named because it's in a U shape. But it's like an autoencoder where we have this kind of compression or abstraction, and then into this latent, and then we're going back up, back to the image. But in this case, it's a lot more complicated, a lot more moving parts. So first, this is, if you're familiar with, is everyone familiar with convolution neural networks? Put your hand up if you're not. Awesome. Alright, so you can see here we have the convolutional, first step is the convolution. So we're reducing that image down by these convolutions, abstracting it. And then up to that, we get to this bottleneck in the middle where our massive image is converted back to this vector of 1,000 size vector. So that would be like a bottleneck and the compression of reality. And then we're upsampling using, maybe not covered in school, but a deconvolution where we basically do the reversal. So we have a small image, we're going there one by one with a massive convolution, so that results in the further one being massive. And maybe another thing is the stride length, which is basically how much you move. So you can see here the convolution moves 2 steps at a time, but deconvolution moves 1 step at a time. So that basically just saves, well, it dictates the size, so it gets smaller faster, and it also saves us memory and speed. Now, of course, we're just looking at images here. Where's the prompt? Well, the prompt is a different type. It's a conditional unit. So we add in between each one of those. Each one of those blocks you saw before was a residual resonant block. Sorry. So in between those resonant blocks, we have this type, basically transformer. So this consists of the self-attention and cross-attention. I won't go into that too much, but that's where the magic goes to. So as you can see here, we get our prompt, the latent. So we get the clip, converts the prompt that you've entered into this latent. Then this gets entered to the transformer, which is of course the latent of the noise. And these get processed together. So how does, well, there's two layers, there's the cross-attention and there's the self-attention, but we're going to cover the cross-attention because it's more meaningful in this case. So cross-attention is made up of 3 parts. So we have Q for the query matrix, so each one of these is a matrix. We have the query matrix, K for keys, and V for values. So you can see here the queries are made from just one layer, a linear, normal linear layer from the noise. Then the prompt is another layer, gives us the keys, and a different layer gives us the values. So we we multiply the query by the keys, and then we have this softmax function, which is basically this compressing it between 0 and 1. So it's like a decision. You can think of this as a decision without getting too much into maths. It's like making the decision of this, because remember we're multiplying 2 matrices and we're refining, it's like a covariance matrix. Not exactly, but we're trying to find which bit of which matrix is more meaningful. So we have this softmax layer which then tries to tell us this connection here is meaningful, this one's not. And then we have this vital thing called a residual connection. So maybe, if you remember before, we weren't predicting the image, we were predicting the noise. So this kind of same concept was not the same, but the same kind of idea, paradigm plays in here, where we're not taking just the output of our model, we're combining the output that we process with the unprocessed values here, or much less processed values in this case. So that will give us a lot better memory. If you're familiar, in my last workshop we covered the recurrent neural networks and we found out why this vanishing gradient problem is so bad. And by basically skipping processes, we kind of forget what we did before, so we reverse this kind of chain of gradients that happens in this vanishing gradient problem. Is everyone familiar with the vanishing gradient problem? I can go over it quick. Okay, so if we're a recurrent neural network, we're repeating the neural network over and over again. So in a normal neural network, we do the back propagation once, forward to back. But a recurrent neural network, because it's repeated 5 times, it's like extending your one neural network 50 times, or how many other times you're doing it. So each one of those iterations, you can imagine you're building up error. So that basically means that small gradients get even smaller, bigger gradients get even bigger. So vanishing and exploding. And this basically bypasses some of those steps. Or kind of, we've got a mixture between bypassing and not bypassing, and that makes the effect of those repetitions less. So as I said before, we do 100 steps of the unit. I think that was a lot. Any questions? Yes?
When you actually, so how you mentioned that the model works rather by reducing the noise, right? So would that mean that your brain data set would contain noise rather than actually
we're predicting the noise, not the image.
So how would you train
To predict the noise. Because you remember the training data is real images, right? So you're applying noise onto the image you found, so you know what the original looks like. So then when you're denoising or predicting noise, you take it away, and hopefully that noise you took away makes that picture look more like the original. That's it, because you got the ground truth or the value, because you augmented your image in the first place, you already know the ground truth, so you're just heading to that ground truth. The same process, it's just instead of outputting the image and having to remember everything, you just output the noise and take it away. Anything else?
What is noise?
Noise?
Noise.
Was like you saw on the slides here. So you can see the bottom image of Shrek, nice and clear, and we have this like fuzzy grey on top of it. So Gaussian noise is basically a very like chaotic function that you add on top of this to make these. So you take the value of that pixel, you give it to this function, it like distorts it, and you get this kind of hazy noise. And obviously it's very hard to predict. And obviously Gaussian noise isn't the only type of noise. I guess there's loads of odd noises. I'm not an expert. It's a good approximate for training, and I guess it's the fastest to compute. Anything else? Alright, so enough of me talking. Let's try it out. I'm sure you've seen are you familiar with Hugging Face? It's a great website. It hosts loads of these massive state-of-the-art models, open source, all for free. Better than GitHub in my opinion. And so yeah, I'll release this. I can paste the link in the WhatsApp to Discord if you like. But let's take some time to have some fun prompting. I think I must have forgot to mention this part, but as you can see, that particular model, basically I did version 1.5, now it's version 2.1, so it's better. Now you can see I have two prompts. You have the positive prompt and the negative prompt. So I think I maybe did this too fast, but when we have this conditional unit, we have our prompt going into the transformer. And conditioning, of course, is look at something basically trying to head towards it. Or not say it. So conditioning is you look at you have your current value, you have your target value, and you're basically trying to head. You're looking at that. The conditioning is looking at something basic. And the positive, of course, you're trying to move your whatever value you got from that first resonant block. You're looking at the latent of, because remember, the image and the prompt are all in the same space. Clip does that for us. They're all the same size vectors. So we can compare those quite simply. by just taking the cosine similarity. So that would be like an angle in this high dimensional space. So that's how they compare it, but basically one side of it wants, I'm not exactly sure how to put one word, but the positive of course is trying to reduce that similarity, make that image closer to that prompt whilst denoising it, and negative tries to get away from that prompt. So we're denoising at the same time as we're trying to head closer to out of our latent. So that's why our resonance basically denoise and our transformers go closer to the prompts, or away from them. And we'll look at just after the break, we'll look at are we limited to text or is there more in it? Yeah, so the clip does the whole sentence. So it doesn't do, like, are you maybe familiar with like word to vector? Yeah, so that only does one word to one vector. But there's a thing like but these are basically, they're pooled versions. So they still convert a word by each, but they're pooled, you have a layer after that which basically takes them all in and combines them into one sentence.
So it says one vector.
Yeah, I'm not sure what exactly clip uses off the top of my head, but yeah, it looks at the whole sentence. But the clip builds on top of the other model. It's probably like Esper or something version of that, which but is like a better version of word to vector because it's contextual, so it looks at the surrounding ones at the same time. And then so you have this pooled version, and then I'm guessing they basically don't really talk about the paper that much, but the clip basically leverages that, but does all this processing to fine-tune our text to do these images at the same time. Oh, that's interesting.
So is this trying to figure out a good kind of
Oh, I guess not. That's interesting. But you could try like a whole sentence. If it is interesting, the one that prompts that you change one word slightly in between the two, and then that's how you get very. I thought that was quite interesting. Oh, it's exhausting.
I mean, hey, everyone needs an exhaust. Do you have any prompts?
I want got two.
Oh yeah. Two exhausts. And it looks like an actress.
Some like US only shit like that.
Or for the drone doesn't exist.
Sorry?
Do you have any prompts?
Was there because of painting Shrek?
Sure. Well.
Let's see how close you get to one. Because this website, I don't think it allows you to do the seed. But basically there's a seed that does the more display stuff.
What is that? So you get to do the type of
There's lots of shit that goes on this. If I had my nose even then.
I mean, it's like there's too many branches.
Yeah, because I basically I didn't want to do everything at once, so I wanted to do step by step. Introduce this. And I guess I didn't introduce everything.
Slowly lower it down.
Yeah. So spiral spin. Are you guys trying?
One of the ones they were quite funny.
did you guys, any interesting findings? Sorry, what's your name? Elvis. So I always found that you have your positive prompt and a negative prompt. So he found if you put, was it Earth in the positive and the same exact word in the negative, we still had a picture of Earth. Right? So it doesn't cancel out like what? So maybe it puts more emphasis on the positive side. I don't know. And what do you think? Your name at the back? Your name at the back? What's your name? Suri. So Suri wasn't sure what to enter for a prompt, so she didn't put a prompt. We had this seed, we just press generate, and we have this random room image out of nowhere. Right? So that's an example of unconditional prompt. We're not conditioning anything, we just have some noise at the start, and the computer, I guess, within that noise, saw some room or some problem, and then started denoising it. I don't know, Drew started doing more complex sentences of what was it? Robotic cows and stuff, so we had some like creative suggestions there. So then this pretty cool website, learnprompting.org, and that basically tells you, that has all these different techniques of what to write in that prompt. You can check it out later yourself, but there's loads of different techniques from this unconditional prompting to these conditional prompts of whole sentences, and even this negative, positive. All have different techniques. And interestingly, it's not very natural speech. It's not the best results I'm getting from I want a picture of a cow with robotics arms and legs. It's more like cow, robot, legs. So that is more condensed, much more big use of commas, semicolons, stuff like that. So it's more of a list of just words which have some kind of semantic relation between them. But it's not always the best results, for whatever reason, don't actually have this standard English form. So, I'm sure you've heard of ChatGPT, and if you're lazy like me and aren't creative enough to create a prompt, you ask ChatGPT to do that. So I asked it, write me a Stable Diffusion prompt for Hogwarts, and we got this great one out here. Interestingly, ChatGPT doesn't know the difference between like Stable Diffusion, DALL-E, and then the other one. It gives a prompt. You can see here that the ChatGPT isn't really up to scratch with its prompting. It hasn't been on prompting something at all, and it's doing basically what like a natural speech, right? What you'd actually tell a person to do. If you go on the website, you see that these like being and things like these verb wouldn't make the model better. It just kind of takes up space and less adjectives. So maybe I'll go back quickly to explaining this. But basically the random seed as well, we start from a random number and that creates the first random noise. So that's completely random just from a number. That Gaussian noise basically out of nothing. You give a number, you give this a random noise, and that's why each time we rerun the model, each one of those four boxes have a different seed and a different image. You can have the same prompt and you press generate again, you're going to have different images because that number, the seed, is different. So technically that means you can have basically infinite images from every prompt, so you can have millions of robotic cows or something. So what's the current research like? Oh, you may have seen. So fine tuning is basically doing some extra training at the end. So I don't want, I don't want this certain style I want a Disney style, Archer style, like a cartoon or the arcane series. And basically we give it more examples of those images at the end. Usually you need like a couple thousand. And that model, everything you enter to that prompt is then going to be into the style that you've given it. So some examples here, also on Hugging Face, are the Latent Diffusion, which interestingly does all three of those styles. You have this Pokemon model, and interestingly also have this Japanese one, where they, instead of using the standard English clip, they train their own clip on Japanese text. So now it's basically Stable Diffusion, but instead of your English text, you can give it Japanese text. And maybe I briefly mentioned this before, but we don't actually have, we're not limited to just text prompts. Transformers are flexible now, that as long as that query matrix, or sorry, the keys and values matrix, has the same size, then we can use whatever we have before that. We have that layer that converts it to that size number. So whatever we have before that, we can have different layers for each modality and still get the same key and value. So basically what that means is that we don't only have to condition on text, we can give it another image, or we can give it like a highlighted area of the image, so we want to focus on this part, or some kind of symbols, kind of the same thing as text. But basically we're not limited to text or whatever. The biggest problem is just putting whatever you have into the same vector space as your images. So whatever goes to the same space works in this one. So an example of this is image variations, right? Instead of we had the random noise from the seed, and instead of saying I want a picture of Jacob Dalek because it was never seen a picture of me, I gave her a picture of me. And it wanted to make another picture of me, so from that random noise, it looked at my picture, I wanted to map that random noise, something looking like my face. So you can see here, these two guys on the right are me, somewhat similar. And that's also available on Hugging Face. So we've all got loads of types of these generations. We have this conditional one we did, just a prompt. We have the unconditional, which we didn't have a prompt, we just press generate. We have these image variations, given a picture. We have image to image, which is somewhat similar, but we give it, instead of giving it a random noise, we start by giving it an example picture in the first place. And then we give it a prompt, so you give it a picture of Shrek or SpongeBob, and then we say make SpongeBob green, then the output is going to be a green SpongeBob or something like that. We also have this image in painting, where instead of giving an image, we have this, we give an area of the image that we want to focus it on, and then it only looks at that part of the image. Only change that part of the image. It looks at the whole image, but only change that one part, and then give it, like highlight my hair with a prompt, make me ginger, and now ginger hair. Now image extrapolation is basically if you have an image and you basically make it bigger, you have what's around the border of the image. Super resolution is kind of the same thing, but just trying to make the resolution, the pixels within, generating pixels within the image. So there's this cool research paper called Prompt to Prompt, and it focuses on these editorial prompts. So you can see here the original prompt is a photo of a polar bear sitting, and then for our editorial prompt, we're adding this minimalist drawing, this description, minimalist drawing of a polar bear. The interesting thing is you can see you have a polar bear sitting with his front two paws in a certain pose. And then by just adding the two, that description, we've taken that picture, like the polar bear still sitting somewhat in the same pose, and we've just changed the whole style. But with that pose of the polar bear, and maybe the color, the pose, the composition of the image is the same as your original, just it's been changed. And this is and the cross attention that we covered in that transformer is what allows us to do that. So if you remember, we had those value matrices. Sorry, the key query matrices. So the one at the top originating from that noisy image. So each, when we combine it, each word of the prompt has its own matrix or cross-attention map. In this case, we were visualizing it by another method. And as we added those two words, minimalist drawing, we basically just inserted, we're taking the same kind of maps that we had before, but now we've added two new ones, or we've taken one away, just spliced them together with these new ones. And now that's what conserves the composition of the original photo, but we've inserted a new style in the middle and slightly changing that photo. And this focus added some more attention onto that aspect that he wanted. And this was my master's group project this year, and we compared basically three methods. So the standard prompt engineering with basically clip embedding mask and this cross-attention control, which was the splicing of cross-attention maps within. So our goal was to not, we have all these different style models. We're changing from anime style to realistic to something else. Also, there's maybe on Instagram. But our goal was to go deeper than that. We don't just want a style, we want to change the cultures. And why is this good? Well, imagine a book written in English, and for a Japanese audience or an Arabic audience, that picture might not be representative. You know, you could put the text into Google Translate or something similar and allow them to read it, but maybe they don't know what that certain, maybe an apple looks like. So maybe they have a different fruit in that culture. And so we want to translate those images as well. So that's what we were exploring. And our clip embedding mask is it's a method that basically transforms our latent prompt before we give it to the model. So we give it the prompt, and we have this latent vector, this big matrix, and we basically we combine that with the embedding of the word of the culture. So like we give it the word Indian or Arabic, some kind of culture. We generate the prompt of that. Then we basically add it onto the original kind of prompt that we wanted in the first place, and it basically makes the original prompt in that certain culture. So you can see here we had more of a white man on the picture A, B is Japanese, C is Arabic, and D is Indian. Now, of course, this goes a lot further in most recent research, where we have kind of abstracting every different concept. So we have shape, semantics, sketch, style, content, intensity, palette, all these different aspects of the image, so many different conditions. And this basically allows us amazing customization. So this would be amazing for any designer. Instead of having to draw it, maybe I look at these style of pictures, but I like this kind of style, artist style, but I don't want it in this form, I want to sketch something else. So that allows you incredible flexibility, and although theoretically it's still possible with the right prompt to get these aspects, people aren't used to prompts. Prompts are still quite new. As you can see, we're only started learning about them. So the industry standard is more shape, styles, etc. So we have people interact with the model by this way. Now, of course, we're not limited to images. Alright, a video is just a series of images. So we can generate image by image by image and create a video. Of course, this takes a lot longer than 1 minute of the image, but you can imagine the results are pretty great. And a similar thing goes for 3D models, where there's this thing called neural radiance fields, which you think of as basically a bunch of lines forming a 3D shape. And instead of working on the image, all the values of the pixels, we're working on the gradients and the placement of those lines. And that's how we use the 3D models. Of course, they're not real 3D models. You can't. There's a big step from these lines to get to a real model that you can import into your computer, whatever 3D editing software. But it's a step in the right direction. Now, there's lots of big legal battles now, because we've given it millions of data all over the internet. Well, Leon 5B was the data set they used for Stable Diffusion. I think that's 5 billion images. So you can imagine what portion of the internet that doesn't, how many artists work, how many articles contributed to that source. So artists aren't happy about it, because now they're going out of business. Someone, instead of telling the artist, I want this painting, or I want Shrek, I want you to paint me Shrek in this style, they're now, you could just go on Stable Diffusion and get 90% of the way there. So they're not happy about that. And so we have lots of lawsuits of, is my work copyrighted, or sorry, is my AI is close, trained from my work, do I own the rights to that generated image or not? And of course there's other aspects, like we trained it on lots of English prompts, but the performance of our language is terrible right now, because there's not enough data on the internet, or maybe that culture doesn't have as much data available because it's more smaller. So there's lots of ethical aspects of that. Any questions about any of it at all?
When you say you create a 3D model, is it just another video since you can't actually?
No. So the 3D model, well, it's called Dream Fusion. I think it's by a team at Google. And they used this, basically I think it was OpenAI or someone else basically had this based on these kind of vectors, these neural radiance fields, which instead of generating 3D models, so you give it a text and it generates these 3D models by basically a series of lines. So you have lines, I guess you have a different color for each line, but the lines basically form like some kind of shape.
So what's the difference between, say, a video or a squirrel?
Well, because videos, images are all pixels, right?
Yeah.
But 3D models, it's not a voxel. So voxels are like 3D pixels, right? You have like a Minecraft or a cube structure. This is different. This is actual lines. Imagine like a 3D sketch. So maybe that's enough theory. Let's get on to some coding. You've already got, hopefully, on Hugging Face. To download it, you may need an account to generate the token. But I've made basically a simplified code version, so you won't have to go into all the PyTorch details just to run the model. And it's available on our GitHub page. So if you just go on GitHub AI sub and then do workshops 2023, or I'll paste the link in the chat as well. And I've basically made this notebook generate image that you can open using Google Colab. I think that's probably the easiest way. And generate an image within 1 minute, just as you did on Hugging Face. Now you're doing it But yeah, the goal was that we have this defined clip and Stable Diffusion, and all we had to do was import it, run it through this code, and then we could start playing around by editing this clip embedding here. So we have the clip model be embed the text, which is generate that latent, and this we had an unconditional one and a conditional one. So the unconditional one is basically the noise, and the conditional one is your prompt. It's unconditional because we're not given a prompt, so it's completely random depending on the seed that you set at the start. So we give that a seed, and that's what generates the noise in the Stable Diffusion Model. We also have these other parameters called guidance scale, and that's how close you want to condition, how hard you want to condition on your prompt. So the higher the guidance scale, so there's this thing called context-free guidance, which is a method of conditioning. And the higher that value is, the lower, the closer the finishing criteria is. Right? So that you're forcing the model to go to have the latent of your generated image as very similar to the latent of your prompt, and only that's when you finish. So the higher the value, the less creative the model can be. Right? So you have to have basically it's a good value, but yet there's like a balancing act. With too little, you're going to start these weird kind of blocky things where the models try and be too creative, right? And we don't like it. Or if you have it too far, then it's trying to be basically too realistic, and it also becomes just like over sharpened. You have these like just very too contrasting colors. So you have to find the right step there. And also the amount of steps is how many times we repeat that unit we had in the middle. Usually around 100 is a good value. Most of the websites use a lot less to save on computing. Doesn't make that much of a difference. After like 50, it's basically the same. But yeah, if you try and do like 4K images, then you probably want 120 steps. If you're only doing like a small image that you don't have on someone's phone, then you probably don't care. And then also try to, so remember clip, we can embed images as well. So we have this image of a polar bear in the GitHub folder, and that is basically going to go through the slides. We're going to basically embed this into a same size vector as our prompt, and give that for our conditional instead. So it's going to condition on our image. We're going to generate another polar bear. Interestingly, this uses version 1.5, and the image variation here isn't that great. If you give it, like when we were testing it before, the polar bear wasn't good. It was terrible results. But the variation, so the generated images were quite good. 2.1 improved this, and the image variation is actually quite useful now, along with the addition of those like negative prompts. So, well, these things are like going insane right now, so that's why there's so much resource, hard to keep up with. So I hope I gave you at least a general overview of how this works, and demystified it.